And here we go. Okay, I want to start by talking about what you just watched with the Fibonacci sequence. I chose those two videos because I think they demonstrate um, why the Fibonacci sequence is really interesting and the golden ratio is really interesting, but also they come from a science-based background. If you look for videos of the Fibonacci sequence online, you are going to find a ton of them that are just full of random pseudoscience that will tell you that the Fibonacci sequence is proof that aliens built the pyramids, or they'll take like proportions of people's bodies, like our finger is like a 1 and our arm is like a 2 and your torso length is like a 5, um, and so there's a lot of pseudoscientific garbage out there where people have taken the Fibonacci sequence and the golden ratio and just like attached whatever random thing they were interested in by cherry picking things out of that number sequence. So you have to be kind of careful how you apply this, and you're going to see lots of stuff out there that talks about this that's just like not supported scientifically. But I like that these ones are, and they talk about the background of it and some of the interesting stuff about it. The packing of seeds is really cool. So if you look at a head of a sunflower, what's a really nice example because it's big, or a pine cone, they are those things are actually evolved to be as efficient as possible. So this is a really neat example of evolution in action, that a sunflower is going to do better if it can pack more seeds into a smaller space. And so it uses this sequence and this ratio in order to fit as many seeds into that space as possible, and thus have as many chance to have those seeds spread and grow new sunflower plants. Same for pine cones. So it's actually an efficiency thing. The most efficient plants did better than less efficient plants, and therefore through natural selection you see that those are the ones that survive. So that's why you see that mathematics show up, because of the evolutionary pressures in the natural world, which is, I think, pretty cool. Excuse me. So when we're talking about the Fibonacci sequence just in terms of numbers, we're just looking at a sequence. We can't actually use our normal system of arithmetic or geometric general terms. That's not going to work for this, because in this case what we're doing is we're adding the two previous terms. So our first term, there's nothing before it, so it's just a 1. Our second term, there aren't two terms before it, so there's just a 1. Our third term, you add 1 plus 1 is 2. Our fourth term, you add 2 plus 1 is 3. Our fifth term, you add 3 plus 2 is 5. So you always look at the previous two terms and add them together, and that's how you get your new term. There is actually a way to write that, though, a general term. So we say, okay, the general term for the Fibonacci sequence is as follows. What you want to do is add two numbers together. Okay? Now, how do we describe those two numbers? Well, the first number is going to be the one that just came before. So if Tn is one of our terms, Tn minus 1 is going to mean the term just before that one. And of course, you add also the one before that. So the one before that is going to be Tn minus 2. So this is an example we call a recursive formula. What it does is it tells you what the first two terms are. So term 1 is 1, term 2 is also 1, and then it tells you for the ones that come after that, what do you do with it? Well, you got to grab the terms before that. So if I say, I want to figure out what term, let's see, 1, 2, 3, 4, 5, 6, I want to figure out what term 7 is. Well, what do? Well, I add term 7 minus 1 and term 7 minus 2. So what are those? Well, term 7 minus 1 is 6, so that would be term 6. And 7 minus 2 is 5, so I'll add term 5. Term 6 is 8, it's up there above. And term 5 is 5. So my seventh term is going to be 13. Okay, so that's how we use these recursive formulas. They use terms to refer to the previous terms that are in a sequence, and that allows us to get the new ones coming up. Another example of kind of a weird one, this one isn't recursive, but for this one, you may say, how do I get this one? It's kind of like cubed, but I'm not really sure. So this one, you say, I take my term number, say my first term, I take a 1 and I cube it, but then I also add my term number minus 1 to that. And that's how I can figure out this sequence. So that's a really tricky one, and one you might have a lot of difficulty just coming up with on your own. I'm not sure I could come up with it just on my own. So I just want to go through a couple definitions here. So recursive sequence is a new term we need to be familiar with, okay? So if we're looking at an arithmetic sequence, like the formula that's up here, we can figure out that, oh sorry, not arithmetic, geometric is what I meant to say. A geometric sequence. We can figure out from that, we're starting with a 3, so that's right there. And then this 2 tells me every term we're going to double it. So we go from 3 to 6 to 12 to 24. So that formula tells me what my sequence is going to be. Now when we talk about that kind of formula that we used, our general term formula, is called an explicit formula. It's called an explicit formula. And it can be used to calculate any term in the sequence. We don't need to know the previous term or anything like that. We don't need to know what came before. As long as we have that general term, we can find it. So that kind of thing is called an explicit formula, where you can find any term without having to know what came before it. The kind we're looking at today is called a recursive formula. So we give you the first term. You have to say what it is in a recursive formula. You have to say the first term. And then each term after that is given by an expression that uses the previous terms, the ones that came before it. So we tell you the first one, and then we tell you how the second ones depend on the first one. So this isn't a new kind of sequence. You can use a recursive formula for arithmetic sequences. You can use a recursive formula to describe geometric sequences. So you can use a recursive formula to describe other ones, like the Fibonacci sequence. So a recursive formula is just a new way of describing what the stuff we already knew. It's just a different way of describing the things we already knew. So if I want to write this exact same one that I have above here, this formula right here, that's my general term that describes the sequence right here. If I want to write that as a recursive sequence, here's what I do. I have to write the first term first. So I'm going to say T1, that's my first term, is 3, because that's the first term in my sequence. And then how do I describe the next terms? Well, I say, well, after that, I'm going to double each time. So I'll say, to get any term, I have to take the term before it. Sorry, that n minus 1 is not turning out well, and I want to make that very clear. I got to take the term before it, and I need to multiply it by 2. So that tells me, okay, my first term is 3. For my second term, I take my first one and I multiply it by 2. For my 10th term, I take my 9th one and multiply it by 2. For my 100th term, I take my 99th term and multiply it by 2. So this is describing the exact same sequence of numbers, but it's just doing it in a different way, in a recursive way. Here's an example. It says a sequence is defined recursively by this stuff. So let's see what we got here. We've got our first term right there. First term is going to be 3. And then we say, okay, to get a later term, you take the term before and you're going to add something to it. What are you going to add to it? The term number squared. So let's get our first 4 terms in this sequence. So I know my first one is 3. I don't know what my other ones are, though. So we're going to have to figure it out. So let's figure out term 2. Term 2 is going to be term 1 plus 2 squared. So everywhere there was an n, right here, and right here, I subbed in a 2 to get my second term. Okay, so term 1, well, that was already given to me, that's 3. And 2 squared is 4. So my second term is going to be 3 plus 4, that's 7. So let's add that one up here. Now how do I get my third term? Well, everywhere I see an n, I'm going to sub in a 3. So 3 minus 1 is 2, so that's going to be my second term, plus 3 squared. Everywhere I saw an n, I subbed in a 3. My second term I figured out before, it's 7. And 3 squared is 9. So I'm looking at 16. Let's add that to my list. My fourth term, let's do that in green. Oops, need a thinner marker. My fourth term is going to be my third term plus 4 squared. The third term is 16. 4 squared is also 16. So 16 plus 16 is 32. There, so I got my first 4 terms through a recursive formula. I'd like you to try this. So I'd like you to get out your notepad. We're going to try getting the first 4 terms, and you'll already be given the first one. We're going to find the first 4 terms for the following. So your first term is negative 25. Your recursive formula tells you take the number before and add 5 to it. I'd like you to do, just like I did on the previous page, I'd like you to figure out term number 2, 3, and 4. Go for it. All right. So let's figure out some terms. I know my first one's negative 25, so I can put that up here. What's my second one going to be? Well, I'm going to have to put in my first term plus 5. So it's my first term, it's negative 25. And I'm going to add 5 to that. So that's going to be negative 20. Okay. Got 2 terms down. My third term, it's going to be n minus 1, so that's going to be term 2. Term 2 is negative 20, and I'm going to add 5 to that. So that's negative 15. And my fourth term. I'm going to take 4 minus 1 is 3, plus 5. Ooh, that's not a good 5. There we go. Emergency 5 repairs. My third term is negative 15, plus 5. It's going to give me negative 10. Now, you might look at that and say, oh, that's an arithmetic sequence. I recognize that. It's going up by 5 each time. So you might say to yourself, normally when we're used to writing arithmetic sequences, I would write that kind of like this. I'd say, okay, my general term is my starting amount, that's negative 25, plus n minus 1 times the difference, which is positive 5. And if I multiply all that out, I'm going to end up with 5n minus 30. So this is how I could make a general term for this arithmetic sequence. And when we do that, that's called an explicit formula. The one above, up here, that I'm going to circle right now, that's a recursive formula. So they describe the same thing. They're a formula for the same thing, but one is explicit, one is recursive. Okay? Let's do, we got 10 minutes. I want to show you one more, and then we'll talk about stuff to work on for the weekend. Here's our second example of recursive sequences. This one is not arithmetic. This one's actually geometric because it's multiplying. So determine the first 4 terms of the sequence defined by that thing, the recursive formula, and then underneath I want to write an explicit formula for this geometric sequence. Okay, so my first one is 5, so I'm just going to put that up here. And then it looks like my formula says 7 times the previous term, the one before. So term 2 is going to be 7 times the term before, which was 5. Actually, I should write that out fully. So it's going to be 7 times term 1. Because the n minus 1, if we're looking at the second term, 2 minus 1 is 1. Okay, cool. So our first term was 5, so I'll plug that in. So it looks like we got 35. That's our next one. So far, so good. Let's do our third one. That's going to be 7 times t2. So our second term was 35. Oops. And that's 245. Let's get our fourth term. $17.15. Oh, that was a good year, $17.15. Or maybe that was a bad year. Okay, so we've used our recursive formula to describe this geometric series that goes 5, 35, 245, 1750. And now we want to write this as an explicit formula. So an explicit formula means it could, depending on whether it's arithmetic or geometric, we're going to use our standard way of doing that. So I'm going to say, okay, my R value, I notice it's multiplying by 7 each time. And my starting number in my sequence is 5. So my arithmetic formula is going to be like this. The general term is going to be AR to the n minus 1. So that's going to be 5 is my A, 7 is my R to the n minus 1. So there it is. I got my explicit formula. And I can also use this to describe that sequence of numbers. So this sequence of numbers we could describe 2 ways. Explicit formula, as we've been doing previously, or the recursive formula, which we just learned today. Some sequences, like the Fibonacci sequence, we can't describe any other way except a recursive formula. We're stuck with that. Okay. So I just want to talk about stuff for this weekend. So I'm going to flip to our final page. This stuff is on Edsby, of course, but I want to talk you through it. So on Edsby, you're going to find in the homework section, there's 2 videos posted that kind of dig into this stuff a little bit more and explore some more neat and interesting things about the Fibonacci sequence, which is like a super famous one. So I'd like you to check those out. On page 439, I'd like you to try these problems here. And on the mid-chapter review, I'd like you to try these problems here. Now I've posted all of these to today's agenda items, so you can find them quite easily. Of course, though, the solutions are in the content section. So check those if you get stuck, and then message me if there's things you'd like me to go over on Monday. Monday, we're going to be starting in on things called series, which are basically the same stuff we've been doing, but how do you add them all up? Because really it's very useful to know the sum of all your numbers. The penny pyramid, for example, when we did that problem at the beginning of the year, you had to add up all of those rows one at a time. We're going to learn on Monday how to do that in a super fast way so you don't have to add them all up one at a time. There's actually formulas that we can use to help us take shortcuts to add up big, long strings of numbers. And that's what we're going to start investigating on Monday. Okay, so this is stuff for you to work on for the weekend. Work hard, work smart. Message me if you're having challenges or problems that you'd like a hand with, or things that you'd like me to take up on Monday.